Welcome to this explainer on AI Fabric, where we're going to jump right in and deconstruct exactly how Java and Spring Boot applications actually route AI requests. Look, if you're building AI workflows today, you already know the stakes are incredibly high. You have to connect model intelligence to real sensitive application data, but the absolute biggest fear is losing control of your business rules or your security along the way. So today, we're breaking down exactly how that routing happens under the hood, both safely and efficiently. Okay, let's dive straight into the AI Fabric framework, which essentially serves as the ultimate coordination layer between your application and your AI systems. Now, it's really important to note right off the bat that AI Fabric is not an LLM itself. Instead, it's a modular Java framework that sits right inside your Spring Boot app. It acts almost like a highly intelligent traffic cop, focusing completely on coordination. It manages retrieval, generation, actions, and policy checks, all while isolating those capabilities from concrete providers using strict, unbreakable contracts. Think about this for a second. When a customer types in, "I am locked out," it is so tempting to just assume one massive generic LLM call can handle the whole job, right? But that monolithic assumption hides a much more robust architecture. If you just send every single request directly to a massive, expensive language model, you're not only wasting money, but you're also deeply coupling your application's logic directly to that specific model's prompt behavior. We really have to ask ourselves, are we treating every single AI task as the exact same generic problem? Because we shouldn't be. So here is our roadmap for today's explainer. First, the 4 provider concerns. Second, routing by LLM purpose. Third, configuration precedence rules. Fourth, the flow through Spring AI. And finally, number 5, keyless versus live proof. Let's get right to it. Starting off with section 1, the 4 provider concerns, and how we actually go about breaking down that monolithic AI assumption. What we're really dealing with here are 4 completely isolated problems that AI Fabric coordinates on your behalf. Step 1 is orchestration, which is basically figuring out what the user actually wants, their true intent. Step 2 is generation, which is drafting that final, grounded answer. Step 3 is embeddings, where you take approved text and turn it into numeric vectors. And step 4, vector storage, manages all the search and lifecycle operations. AI Fabric deliberately separates these. So for instance, you could use a local Onyx model just for embeddings, Lucene for your vector storage, and then a heavy-hitting cloud provider purely for generation. By decoupling these 4 steps, you literally eliminate vendor lock-in and optimize your costs at every single phase of the request. It's a total game changer. Moving right along to section 2, routing by LLM purpose, which is all about matching the exact job to the correct model. Since those concerns are totally isolated, AI Fabric uses a routing mechanism called LLM purpose to assign specific tasks to dedicated models. Think about how incredibly useful it is that your intent extraction doesn't have to share the exact same model configuration as your final answer generation. You might have one highly specific configuration just for generating embeddings and a totally different one for generating text. This guarantees that every single task gets exactly the processing power and parameters it actually needs, without any waste. Breaking that down a bit further, AI Fabric's purpose-specific routing ensures that a task like structured orchestration goes to a model specifically optimized for intent, something blazingly fast and super reliable at spitting out structured data. For generation, on the other hand, you absolutely want a model with a huge context window and strong reasoning capabilities to properly summarize retrieved evidence for RAG. Similarly, when the task is simply embeddings, AI Fabric smartly routes that to a profile optimized purely for numeric translation. And, of course, if all else fails, a default profile is there to catch any fallback operations. It's all about aligning the specific task with the ideal model profile. Next up is section 3, configuration precedence rules, and how AI Fabric resolves conflicts when they inevitably pop up. With all these different models handling different purposes, we need some very strict rules. This framework builds a clear hierarchy of authority. At the very top, the absolute king is your explicit YAML configuration. That acts as your ultimate policy enforcer. Right below that, you have your developer-friendly annotations sitting directly on an entity class, which lets you easily declare which fields are searchable text and which are just metadata. And finally, sitting at the base are the AI Fabric framework defaults. So if there's ever a conflict, or if you just need to rapidly push a new application policy without having to recompile your Java classes, that explicit YAML configuration remains completely authoritative. It overrides everything else every single time. That brings us to section 4, flow through Spring AI. Let's chronologically trace an actual request journey. So let's trace this exact journey from start to finish. Phase 1. Your Spring Boot app builds the trusted context based on the user's entry. Phase 2. AI Fabric steps in to route the request by purpose and apply all necessary security gates. Phase 3. The Spring AI module gracefully bridges the request. And finally, Phase 4. The Concrete LLM, whether that's OpenAI, Gemini, or whatever you choose, actually performs the inference. The absolutely critical detail you need to take away here is that security, tenant isolation, and intent routing all happen before Phase 3. Your application entirely owns the policy. The provider is literally just supplying the raw intelligence when called upon. Finally, we reach Section 5, Keyless versus Live Proof. How do we securely test this entire provider architecture? To do this safely and effectively, you actually need a two-pronged approach. First, you run deterministic keyless tests to prove the framework boundaries and security gates locally. By utilizing local ONNX embeddings and Lucene vectors, you can validate your entire indexing lifecycle, your semantic search, and your tenant filtering completely offline. That means you're not spending a single dime on API costs, and you aren't risking massive bills on CI/CD pipeline tests. Then, once those hard boundaries are completely locked in, you swap over to live provider proofs. This validates your real-world latency, accuracy, and ensures the model handles your specific prompt shape perfectly against real endpoints like OpenAI or Azure. So, as we wrap up this explainer, I want to leave you with one final, absolutely critical thought for your own architecture. You must always know exactly which system is executing your operation, and you must demand concrete proof of its boundaries. Are you blindly trusting an external language model to enforce your internal database boundary? Because if you are, it is definitely time to start routing those concerns properly. Thanks so much for joining me today, and keep building those robust, production-ready AI architectures.